Now let's go ahead and look at a specific case, the case from Galileo, where he used s of t to equal 16t squared. And if you recall, this is if an object is released at time equals 0 from a state of rest, not thrown, but from a state of rest, then the distance traveled after t seconds would be given by this function, s of t equals 16t squared. Well, first of all, just taking a quick glance at this, you can pretty clearly see 16 is positive, so this is a parabola opening up. Time can't be negative, so we're going to be specifically looking at the first quadrant instead of all four quadrants here. Let's go ahead and look at this at a few intervals. Let's look at this at 0.5, and this again is my time. In this particular case, let's go ahead and look at this in seconds. 0.51, and we kind of have to be a little bit careful how we scale this. 0.5 and 0.51 are very, very close to each other. 0.55 would be further out. And again, this is just a curve sketch. And then 0.6, of course, should be equal distant out here from 0.55 to 0.5 as it is from 0.55 to 0.6. But that's not the important thing here. We want to kind of get this nice and stretched out so we can look at some tangent lines. So again, we know that this is a tangent line opening up. Or sorry, this is a parabola opening up. If we plug in 0.5 or 1/2 into our function, so if we plug in 1/2 into our function, 1/2 squared is 1/4. 4 goes into 16 4 times, so I could plot a point on my graph, let's say s of 0.5, and this would equal the value of 4. So again, this would equal 4. But I want to just kind of note this generically. Now, since this is a parabola opening up and we have positive concavity, I know at 6 seconds this will be increasing as well. So again, this is our position function. This gives me my distance traveled after so many seconds. So go ahead and do a quick curve sketch of this. We'd come up with a point here. 0.51 we're going to say is moving up here. Of course, 0.6 is going to end up here somewhere. So I'm going to go ahead and sketch this in. And this is what we're interested in looking at. So 0.51 would be this value. 0.55 would be this value. And of course, 0.6 is already plotted up here. Okay, now what we want to do is we want to find the slopes of each of these secant lines. We want to find the slope of the secant line between 0.5 and 0.51. 0.5 and 0.55, 0.5 and 0.6. And so that's what we're going to do next. Okay, so to get started here, the first thing I'd like to do is to look at the slope of the tangent line between 0.5 and 0.6 seconds. Actually, it's going to be a secant line. What I'm trying to do is to estimate the slope of the tangent line at t equal 0.5 or 1/2. But I can't do that because, again, the slope is the change in y over the change in x, and at exactly 1.5 my change in x is 0, and so my fraction is undefined, so I can't do that. So to get started here, what I'm going to do is I'm going to estimate it with this secant line. And as you can see here, it's probably not a very good estimate. Okay, so what I want to do is to find the slope of the secant line. The slope, of course, m represents slope of the secant line on the interval 0.5 to 0.6. Well, we know the slope of the secant line is going to be my change in position over the change in time, which is going to be s of 0.6 minus s of 0.5 over 0.6 minus 0.5. Plugging this into my original function, I have 16.6 squared minus 16 times 0.5 squared over 0.1, and I get 17.6 for the slope of this particular secant line. So for this particular secant line, the slope is equal to 17.6. Now I want to go in and do the same thing except for now I want to find the slope of the secant line between 0.5 and 0.55. Whoops. Now when I find the slope of this particular secant line, it's going to get a little harder. I should have drawn this graph a little steeper. But I'm going to get closer and closer and closer to the true estimate to the slope of the tangent line at that particular point. So I'm going to go through the same process as I did down here and find the slope of the secant line on the interval 0.5 to 0.55, and then I'm going to do it again. In this particular time I'll find the slope of the tangent, or sorry, the secant line between 0.5 and 0.51, and we can see here that it's going to be very, very, very close to the actual slope of the tangent line right here at 0.5. So I'm going to run through those steps and come up with these slopes, and you should do the same. And again, these are pretty easy to do. Slope is just change in y over the change in x. So go ahead and give it a shot and see if we can get the same answers here for these slopes. Okay, so catching back up, here I have the slope of the secant line on the interval 0.5 to 0.55. Now this should be a better estimate than the slope of the secant line between 0.5 and 0.6 because the points are getting closer and closer together. So for here I came up with the slope of the secant line to be 16.8. Now down here, my last one that I checked was the slope of the secant line between 0.5 and 0.51. So that's this work right here. Now here I found the slope of the secant line to be 16.16. Now what ends up happening here as I look at this, the slopes of the secant lines are approaching the actual slope of the tangent line. So the slopes of the secant lines are approaching the slope of the tangent line at 1/2. That's pretty interesting. Now from calculus, and eventually we'll know how to do this. What just took us a long time, we'll be able to do in about 30 seconds in a few weeks. From calculus, the actual tangent line slope is 16. So we got pretty close using this method of finding the secant line, kind of going after that idea of rate of change to come up with this. So this is pretty close. This is pretty good. What could we have done to improve this estimate? Well, first of all, we could have gotten intervals that were even closer. So instead of just 0.5 to 0.51, we could have gone 0.5 to 0.500001, plugged them into the same formulas using the same idea to come up with an even better estimate. So the upshot of this is, what is our takeaway from this? As the time interval t1 minus t0 approaches 0, meaning as my time gets closer and closer and closer together, okay, the average velocity approaches, and again this arrow means approaches, the instantaneous velocity. And that's exciting. That's neat. So that's kind of our big takeaway point from this. Now, as this other point up here, as these points along this graph up here, as they approached this very, very important point, and again I cannot use my highlighter, so as these points got closer and closer and closer, and I found those slopes of secant lines, the slope of the secant lines approached the slope of the tangent line at this fixed point. So again, that's kind of the takeaway that we want from here. In our next section, section 2.2, we're going to be looking at limits and looking at both a numerical and a graphical approach. And actually, we've looked at a numerical approach twice. We looked at a numerical approach up here in this table, And we also looked at a numerical approach here with this graph. Note that we only approached this from one direction, whereas in the table up above we approached from two directions. Hope you're looking forward to section 2.